Hello, this is Hit Pause, a podcast made in San Francisco with more questions than answers. And welcome back to Hit Pause, a little podcast to think about life and science and business. We are starting season 2 with the first episode with Jeff Scargle, a friend of mine who is a scientist, astrophysicist actually, at NASA AMES. Good afternoon, Jeff.
Hi, Hervé. It's a pleasure and an honor to be here. I appreciate it.
Thank you so much. We're innovating here today. This is the first time that I'm having someone to have a conversation on Hit Pause. So thank you very much for participating in this new adventure.
Sure. I'm looking forward to seeing where it leads to. So.
Absolutely. This is a little bit of a conversation more than an interview. You and I have prepared this conversation a little bit, but we're innovating here as bringing a new format, a little bit of innovation in the format of our podcast with conversation of people, friends, colleagues, people of the Silicon Valley and beyond, to talk about themes of interest to the arc of what we're exploring. In the first season, we talked about media and the evolution of media. In the second season, we're exploring a little bit about the human psyche and the construction of the psychology of people that are receptors and emitters of messages in social media. And for the second season, I wanted to bring something more interactive. And so we're innovating today.
Yes.
You're the first person coming into the conversation. Thank you.
Well, again, I'm honored to.
So for our audience and auditors, Jeff Scargle is a personal friend of mine and has been for many, many years. Jeff, you're an astrophysicist at NASA AMES Center. Tell us a little bit who you are and what you're doing there.
Sure, yeah. NASA AMES Research Center is one of the NASA centers. It's the smallest of the NASA centers. It's the only one in California. JPL, our rival, is not technically a center, but that's beside the point. And we bill ourselves now as NASA in Silicon Valley, I guess. So that maybe is appropriate too. Do I understand that one of your themes is the Silicon Valley background and milieu? Am I wrong about that? That most of what I heard in the first season was oriented toward Silicon Valley?
There is Silicon Valley for sure. This is where we're both grounded at one of the hotbeds of technology innovation. But what intrigues me most to explore are the themes and the collisions sometimes, and the interactions for sure between the human psyche, the human psychology, who we are as human beings, and those machines, those innovations that we are pushing in the Silicon Valley ecosystem. And you bring, it's a pleasure to have you for the first time and as a conversation here, because you come from a slightly non-traditional outlook on the Silicon Valley and the world of true science, astrophysics, actually.
Yes, I hope we have time to go into that in some detail, because Silicon Valley and the high-tech industry has had a big effect on astronomy and astrophysics over the last, 50 years or more, coinciding with my career. And that's something that I think you'll find interesting, but maybe we'll get into that later on. Basically, I'm a research astrophysicist. I love data. I consider myself a data analyst, and I like to think that that's where the science really takes place. Other people make observations and slave away collecting data. Theoreticians slave away making abstract theories, and where the scientific progress is made is when the two are brought together. And I see myself as bringing those together and extracting the information from the data that's relevant to the background science. I started off my PhD thesis. I was a graduate student at Caltech when Caltech was, and still is, one of the great institutions of both mainly observational astronomy. And my thesis was on something called the Crab Nebula, and that may or may not mean anything to, if there are any amateur astronomers listening, they may know it's also called Messier 1. It's the first object in Messier's catalog of objects, and it's a remnant of a supernova from the year 1054. Well, I don't want to go off into too much detail or we'll never end this conversation, but it was a fascinating thing, and it was near the center of this nebula were rapid motions of features, and as I measured these features, it was clear these things were moving at a good fraction of the speed of light in the center of this remnant of a supernova that was 900 or 1,000 years old. And it was at the beginning of an era where pulsars had just been discovered, and the Crab Nebula was a really hot topic. And but after a while, I got kind of tired of it, and I wanted to get away onto other things. And I was interested in extragalactic objects, galaxies that vary in brightness rapidly in time, and in a way, the sort of thematic evolution of astrophysics over my career has been, at the beginning, the universe was thought to be a calm, serene place with everything moving in its orbit like clockwork. It's sometimes called the clockwork universe. And more as NASA went into space and we got new observations in different wavelengths, it became clear the universe is a highly dynamic, changing thing. There are explosions, galaxies exploding, supernovae, gamma ray bursts are one of my favorite things, that are enormous explosions that are still not really understood. And so I developed time series analysis methods, statistical mathematical methods for analyzing data from gamma ray and X-ray observations of these sources, merely thinking I was distancing myself from the Crab Nebula, which, by the way, was considered a standard candle, a non-variable source that every time we went into space to measure new wavelengths, radio, X-ray, ultraviolet, gamma ray, the Crab Nebula was the standard. But the Fermi Gamma Ray Telescope that I'm working with discovered that's not so. The Crab Nebula has fantastically bright flares of radiation. So in a way, it's sort of the arc of my career. I started with the Crab Nebula, tried to move away from it, and it kept crawling back toward me, I guess is a way of saying it. And so I'm now ending up analyzing time series data from the Crab Nebula, and to me, that's a very, I don't know how to put it, but I hope a lot of other scientists have that same thing, where something early on in their career comes back in a new light and sort of falls into place. So I'm sorry, I'm rambling off, but that's kind of my interest. It underlies my interest in data and trying to understand this dynamic universe that's just full of these fantastic new things that we just had no idea about 20 or 30 years ago and are now the hot topics of astrophysics.
That's fascinating story, and thank you for sharing that. We've been friends for a long time, but I never really asked you all those questions.
Yes.
Deep around a nice dinner and French Bordeaux.
Right.
Do you think that the recursivity of the Crab Nebula from when you started your career and then back is caused by the advances in data science, in the tools, instrumentation that gives you more and more data? And then for every new discovery, there's always something new to be dug deeper. What do you attribute? You say it's not uncommon in your field to see this recursivity.
Well, I'm not sure how common it is, but it's a good question. I would use the word enable. I think the technology and and so on has enabled, certainly it's enabled the kinds of data that I work on, and allowed these measurements. I mean, just the idea of measuring gamma rays from objects in the universe is a fantastic advance, and is based on development of technology that you're familiar with, transistors. In fact, I was going to say, I thought maybe you would ask me this question: what is the most important technological development in terms of facilitating astrophysics over your career? And see if you can guess what my answer would be. You probably know the hardware, but
interesting. So I would say maybe massively parallel computing, or what is really not necessarily changing are the world of discovery, science, the stars, and everything that is out there, but the lens through which we apprehend, and the power of the lens through which we can apprehend the same phenomena. That probably would be my answer to your question, since you're turning the tables on me.
Yes. Well, I'd like to do that. Well, of course, there are many different things, but if I had to pick one, it would be something that I think you wouldn't think of or mention, and that is the charge-coupled device, the CCD. When I started as a kid and went to graduate school and so on, the only thing we used were photographic plates. That's how astronomers, I mean, a long time ago, people only looked through telescopes and maybe made drawings. Galileo made drawings, but so in the early 20th century, photography was the big deal. And I still remember going up to Mount Wilson Observatory and getting some really high-tech measurements on a strip chart recorder. And I got the data off by drawing lines and measuring positions on a strip. You may not even know the term strip chart recorder, but a roll of paper with a pen on it. You've probably seen them in old movies. But over, and one of the key things was that it was known that we would never learn anything about objects that were fainter than the 21st magnitude. That's an astronomical term. It's a really faint object because the background brightness of the sky is 20-some magnitudes per square arc second. But that turned out to be completely false. And the reason is that charge-coupled devices, CCD cameras, are linear objects. They can measure photographic plates are nonlinear, and you get very distorted measurements. And so really almost everything that we have learned about astronomy, about the universe, has come from CCDs at the focus of a telescope. Now, of course, digital data processing, data acquisition, all the way through to machine learning and deep learning and so on to analyze and understand the data. Those have been important too. But like I say, if I had to be on a desert island with only one technology as an astronomer, it would be a CCD camera. Like the ones in your cell phone, of course, are infinitely more powerful than the first cameras that astronomers used on the Palomar 200-inch or anything. So that's really, it may seem quaint and odd, but that, to me, that's one of the biggest technological enablers of astronomy and astrophysics.
You talk about the beginning of your career when you talk about that transition, that change. Talk to me about the passion that the young Jeff Scargle had about astronomy and what drove that curiosity about what's beyond the realm of the visible to the naked eye.
Sure. I still remember an early incident in my life was our family was on vacation in tropical Sarasota, Florida, a winter vacation. And there was some kind of a store that had a microscope kit in it. And as a kid, I saw the display and my mind went crazy over the notion that you could put your eye up to an eyepiece and see into another world. And I whined and begged for my parents to buy me the microscope kit. Unfortunately, they didn't. So if they did, I might be a biologist now. But the real step was the Adler Planetarium. My parents took me to a planetarium show, and the Adler Planetarium then was an educational planetarium, not an entertainment laser rock music thing. And it was just a wonderful show, and I just immediately fell in love with astrophysics at the planetarium. Ironically, I also fell in love with classical music because the background music for the planetarium show was the Tchaikovsky String Quartet, which I still love. They played the Andante Cantabile of the String Quartet, and I had no concept of classical music then, and then I became a fanatic. So 2 for the price of 1, astronomy and classical music. And if you want the real passion, if you want to use that word, motivation, it's a simple thing that I think has motivated a lot of astronomers, is the simple notion of looking up at the sky and thinking, beyond the Earth's atmosphere, if I keep on going, if I could see a long array further than the sun or the stars or whatever, what's out there? I mean, that's as simple as that. It's a curiosity. What is above this mundane layer that we populate, that's full of wars and people killing each other and disease and that, to me that's really what underlies a lot of astronomy. It may seem not so profound. It's a curiosity. It's not only what's there now, it's what's going on. What are these dynamical, explosive processes that I talked about? How can that much energy be released in such a short period of time? These gamma ray bursts, they're fascinating. They are one-shot things. They last, some as short as a few milliseconds, some as long as a few hundred seconds. And while they are on, so to speak, they're brighter than everything else in the universe put together, in all wavelengths, but only in gamma rays. They don't last long, so the total energy is not humongous, but it's almost unfathomable in terms of like the output of the sun is trivial, or the output of our entire galaxy is trivial compared to what's going on in a gamma ray burst. We're now understanding a little bit about them, but so how can you resist studying and learning a little bit about these fantastically unusual universal activities and objects?
All right, we're going to take a brief pause. It's a pleasure seeing your passion for all our auditors. As I'm recording this with Jeff, we're on camera, but you should see his passion show up through all of this. Thank you, Jeff, for sharing.
Thank you.
Your passion, and we will explore the imprint of those experiences as a child and the imprint that they leave on us as adults. And so thank you for giving already us a hint of episode 2 of Hit Pause podcast. We'll be right back. And now let's go to a short break to hit pause, reflect, or just continue. And welcome back to Hit Pause in conversation with Jeff Scargle. It's been wonderful hearing from you, Jeff, about what got to light up that passion for astronomy and the Crab Nebula. I want to go back a little bit into your experience of the tools of technology, the tools of the trade, if you will, in astronomy, because you've lived in the Silicon Valley for all that time. And you're married to Phyllis. She has been a marketing exec in the tech sector. So you have seen the development of the Silicon Valley. And because you're not a Silicon Valley startup business entrepreneur, but you're using the tools, What's your outlook on what the Silicon Valley has brought to your field, astronomy, and the tools of the trade?
Well, that's not quite sure how to approach that. The most straightforward thing is what I hinted at in the first session, was tools that are provided that enable what I'm interested in, and using them without regard to material profit or sort of any business sense, or any sense of trying to use the tools to compete with other people. Science, I mean, this is a bit controversial, but to first order, science is a collaborative thing, and there isn't a lot of people trying to get there first and so on. Of course, individuals always like to be the first one to make a discovery. But so what I see is that the tools have been developed by a lot of smart people, like Sun Microsystems developed these wonderful workstations that enable the kind of data analysis that I'm interested in. And that's another, I was sort of teasing you about the CCD as being the most important thing. It's really a bunch of things that are almost equally important, one of which is data processing in the simple way. Again, not just for classifying or archiving data for some other use, or selling data or whatever, but to understand and extract the science from it. And so the tools have developed over the years, starting from just very rudimentary input-output storage and applying traditional methods. And as time went on, new methods were developed, and I participated in that a bit. One of my favorite things is to develop, I guess it's a buzzword now, algorithms, data processing algorithms for astronomy. That is, new techniques for taking a time series, for example, the measurements of these gamma ray bursts or the Crab Nebula or active galaxies over time, and trying to figure out what's going on and the engine that's driving the variability. And one of my I like to tell this story because I have one paper that is by far the most cited paper that I've written. I'm too modest to say how many citations, but it's in the thousands. And I almost didn't publish this paper because I didn't think it would be that interesting to anybody. It has to do with how to do Fourier analysis of data. I don't know if you and your listeners are familiar with Fourier analysis. It's a way of taking time measurements and extracting information about periodic signals, that is, signals that vary in a very regular way over time. And Fourier's methods and the so-called fast Fourier transform that's at the root of a whole lot of things. I'm sure there's fast Fourier transform routines in your cell phone and in your earphones probably, because they're so universal, but they rely on the data you feed them being evenly spaced. And if the data aren't evenly spaced, how do you deal with it? And I developed an algorithm that deals with that has been used all over in fields outside of astronomy and so on. But like I say, it's I see it as a measure of my lack of judgment about the worth of some of my activities, because, like I say, I almost didn't publish it, and it turns out it's really valuable to other people. Whereas other things I've done that I think are really great are ignored by the community.
It's a wonderful story. I'm learning so much about you, even after having known you for decades. Do you think, by the way, that this is a blind spot that we have as human beings, as intellectual beings, that sometimes some of the things that appear to be obvious to us, or vice versa, that are obvious to others or that others see value in, we don't see value?
Yes.
In the scientific field, where do you think that comes?
Yeah, exactly. That's it. partly why I raised the question, because I knew you'd be interested in the psychology of that. And maybe I don't think it's limited to science, but I guess to me, it's a matter of perspective. When you're sort of focused on something and grinding away, you have a different perspective, and you don't see the big picture because you're too focused. And when other people get a hold of your work and apply it to some new area or something, they do see the big picture and so on. And maybe it's just hard to judge yourself, is a way of saying it. Is that a reasonable thing to say?
Yes, there is a psychological theory actually about the bias, the inherent bias that we have as human beings, where we are either undervaluing our abilities or overvaluing them, depending on the point of reference and the body of knowledge that we have about something. Yeah. And interestingly enough, the less people know about a field, the more they overvalue themselves. And the more they know about a field, the more they undervalue themselves.
Yes. Right. There are famous quotes, I guess, of Albert Einstein saying, "I'm really not any smarter than anybody else. I just work harder." Or I forget the exact words, but I'm sure there was a bit of slightly faux modesty there. But
that's right. When we looked at one of the key themes that you and I discussed a little bit as we were preparing this, is the arrival of the internet. There is a myth out there that in the Silicon Valley, we created the internet, we invented so many things, and then with the internet, suddenly a geyser of billions of dollars showed up, and large companies,
yes.
We don't need to name them, emerged out of that. You have been in the field of technology and science that has looked at and always used incrementally the tools of the time. What is your perspective on the internet?
Well, maybe a little bit of historical narrative might be helpful there. When I first started at NASA AMES, or shortly thereafter, I started doing more and more data analysis using something that was brand new then. It was called a time-sharing system on the computers. I guess, I don't know, they were large computers. Maybe they didn't qualify as supercomputers then. But so back in those days, there were central computers. And this was the first time that, as far as I know, that the concept of having remote terminals that had access to one central computer. And so there was software residing on the main computer that I could use in my office and develop data analysis methods and so on. This was all completely before the internet. And then the internet came along, and I just, like many people, saw it as a gradually growing thing. As you probably know, in some sense, people at SLAC and in the high energy physics community and DARPA and so on were involved in the very first true internet systems. And they just grew became more and more powerful. So I don't see it as a sudden appearance on the scene, as more of a growing thing that people really took a long time to understand what it meant. And even in business, didn't take a lot of corporations a while to figure out what the internet meant and what it could do for them, and marketing and sales and so on. Well, how do you and as you know, it's sort of exponentiated into today's the thing that you talk about, social media and selling things, where if you go on your computer and buy something, you're immediately deluged with ads for related things, and it's
deluged and targeted. Yes,
exactly.
And actually, the internet, as we know it today, the internet monetization comes from what was at the time considered an impurity, right? The original business model of Google was to be a search engine for good. And the intervention of Sequoia Capital that invested in the business to add this quote-unquote impurity of advertising to give it the financial means to continue to fuel its growth. arguably, it's an impurity that propelled the internet as we know it today.
Yes, right. And to maybe shift gears a little bit, to me, one of the most useful aspects of the internet is the simple notion of being able to exchange documents and drafts of papers. When I started out, if you wrote a paper, sometimes you made a couple of dozen copies on a mimeograph machine and mailed them out to your friends. And there was a big deal about sending a postcard to someone across the world asking for a reprint of their article. You always said, your fascinating article about such and such is, I would love to read it. Can you please send me a reprint? And so it took weeks or months for that to happen. And it's evolved into a system. I don't know if you're familiar with the archive. Cornell University is the one that curates it. And basically, almost every scientific publication is first posted on the archive. There's no refereeing as such. There's sort of a procedure that weeds out total crank papers, but it's essentially unfiltered, and so you don't have to go through the hoops of refereeing and so on. But it's extremely fast, and within, like a lot of times in astronomy, there's a discovery, a new thing is found, fast radio bursts or some new phenomenon. And within a few days, theoreticians write papers explaining what's going on and post them on the archive. So it may seem just a convenience, but it's actually accelerated the pace of progress in science in general and in astrophysics and astronomy in particular by a huge amount. And that's a big deal.
Do you think that the speed of change and the fact that curation is harder in a world where speed suddenly accelerates? We explored that in the season 1 of the podcast, especially when it comes down to the propagation of malicious news, of manipulation, information. Yes. Is there the same risk in the scientific community these days with having such a speed, or in the scientific sphere, is there enough scientific, brains to really correct or use what I talked about as the boron rods of the social media information distribution?
Yes, that's a great question, and I'm a little naive, but I think in science there's very little of that. This archive in particular, I've never seen something that was clearly a total fabrication, or there have been some papers that I think have the wrong ideas and so on, but that could happen in a journal just as well. I even use Wikipedia a lot, and I consider Wikipedia a more open to fraudulent activities than the scientific archive. But so when I see things, I check them out. If I see something that doesn't seem right, I try to check it out other ways and so on. But no, I think for some reason, self-policing, so to speak, in science works pretty well. Like I say, I may be naive, and I hope maybe you're going to chat with maybe some other scientists later on in this season who might have other ideas, because it's obviously a risk, and there may be arenas that I don't know about it. I consider myself very isolated from things like Facebook and Twitter. I barely know what Twitter is, so I've shielded myself from the horrors of disinformation and misinformation that go on there. So maybe I'm living in a bubble when I say there's almost no problem with false and fake science, so to speak.
Well, the concept of fake science is probably belongs more to the sphere of the political, the societal, and not to the concept of the science sphere itself, by definition, because you're talking about a community of scientists who, by the nature of who they are self-policing at the source, arguably. unless they become politicized and therefore move or get out of the sphere of the science.
Yeah. No, I think the key thing about the scientific method to me is self-criticism and the procedure of trying to disprove something. I believe most science should devote 90% of the time to disproving something and 10% to proving something. In other words, what's the problem here? What's the what could go wrong? What could I have done in my analysis that led me to this false conclusion? And I think it's rare that individuals are that self-critical, but overall, when someone publishes a paper that may be a little bit rushed and seeking a discovery too much in some sense, it immediately gets criticized and read by other people who then may tear it down if it's wrong or build it up if it's right. And that, to me, that's why science is reliable, and that's why, to some extent, medicine is reliable to the extent that it's carried out in that scientific way. It's other fields like politics and I don't know, other things where this intense desire to disprove yourself or colleagues is really part of the whole philosophical underpinning.
We're going to take another break, but I love that we're finishing this second part of our conversation on the relationship between the human side and the self-policing side of science. After all, even a scientist is a human being and has a certain level of ethics and standards, which is defining the field. Thank you, Jeff. We'll be right back. And now, let's go to a short break to hit pause, reflect, or just continue. And we're back with Jeff Scargle, esteemed scientist, astronomer, astrophysicist at NASA AMES Research Center. Thank you, Jeff, again. We talked a little bit about the beginnings of your career and the child magic of discovering science and the stars and beyond. We talked a little bit about the Silicon Valley, the tools of astronomy, technology, and the intersection and your personal use of the internet. I want to look a little bit forward into the future. And to do that, I want to go back to your work as a teacher, as a professor with the San Jose State University and Stanford universities. You've been working with young minds, young students of multiple ages. What does that experience brought you? What is the curiosity that you see in them that you either recognize or that surprises you?
Okay, sure. Let me first clarify. I've never actually been a professor at a university. A long time ago, when I first got out of graduate school, I was in UC Santa Cruz. I was a combination of an astronomer at Lick Observatory and on the faculty at UC Santa Cruz. And I did some teaching there, which I enjoyed teaching undergraduates more than graduate students for reasons I don't want to go too deeply into for fear that some of my my graduate students may end up be listening sometime. But it's a matter of I don't know, excitement and passion there that I found the undergraduates tended to be really interested. It was maybe not their major, and they were taking an astronomy course to sort of broaden their viewpoint or something, and they were really interested, whereas the graduate students saw it as a necessary requirement for a degree or something like that. But then I essentially went into I went into NASA AMES quite a while ago and have been there ever since. I haven't had any academic position, and I think I suffered from for a long time I didn't interact much with students, and I had the sort of snobbish notion that, okay, a student comes for a summer internship and you work with them for a little while and spend a lot of time, and then they disappear, and the project doesn't get finished, or you spent time, and I could have done it myself in 3 days, but I spent 3 months trying to teach somebody, and that was a bad viewpoint. And somehow I got connected with a program at San Jose State University. It's CAMCOS is the acronym. It's the Center for Applied Mathematics, Statistics, or I forget the acronym, but it was a math department program where students could work on a project for a term and solve a problem. And they went around to universities and other, well, to NASA and to a lot of corporations like Verizon at a certain point, and Volvo and so on, and got funding to support students to work on a data analysis or related project. And somehow I got convinced to sign up for this program, and I, again, maybe snobbishly, gave them a problem I thought was unsolvable, and explained the problem to them. And 3 weeks later, the professor and the students came back, not only solving the problem, but going far beyond what I had sort of laid down as the not requirements, but as the kind of the scope of the solution. And in fact, that result, it was a data analysis result, yielded an algorithm, a specific algorithm for analyzing data, which is called Bayesian blocks is the name of it. If you Google it, you'll find it's become pretty popular, and it's used all over astronomy in a lot of different ways for analyzing time series data. And that was a lesson of humility or something for me, because I suddenly saw that working with students can be a really, really great thing. And this professor, Brad Jackson is his name, was in the math department there, was instrumental too. So anyway, and over the years, I've interacted with students and research postdocs and so on at Stanford and San Jose State. And the trend that I see as really important is kind of a interdisciplinary approach in a specific thing. Mathematics and statistics, as well as the science, astronomy, as well as computer science or whatever, that joint programs or joint majors in that. Frankly, astronomers historically have been pretty poor at statistics and mathematics, believe it or not. Theoreticians do their kind of math, but in data analysis, it's been historically, like I say, some very dumb things have been done, and there's basic lack of knowledge. I consider myself a self-taught data analyst and statistician, but nowadays that's not a problem. Students are taught kind of both sides of that fence at the same time. So the really bright students at Stanford in particular, that not only know the underlying astrophysics and science, but they're pioneering developments in things like applying deep learning and machine learning to scientific data analysis. So again, that's a major trend that I see, is that merging of the academic fields into something broader than used to be the case.
That's a fascinating story. I can relate to that in the field of business, where I am on the business side of the technology space in the Silicon Valley, where historically over the past 2-3 decades, you had very clearly defined fields: sales and marketing and engineering and product management. And now more and more, countless stories of corporate successes are built on breaking the silos, either internal or externally. And there seems to be a major theme that maybe I'll explore with others in this podcast around why is it that when we start from looking at the world from a certain lens as human beings, we by definition have either a unique lens of focus or we have blind spots? And it's only innovation and widening the field of view, literally, to use a scientific term, comes from breaking those mental silos. So there is, to me, an intrinsically human story behind innovation in whatever fields. Mm-hmm. Would you agree?
Yes, absolutely. Would you say that, like in business, you hire a lot of new people in your job, I assume, is it typical to find interdisciplinary training, even joint majors in broader fields than just MBAs? Or?
Yeah, it's a good question. I would say that it's typically never possible to hire the one person for which you have a mental idea in mind as a hiring manager. Uh-huh. And therefore, because you're designing a position with a certain business objective in mind, so you're defining how that person might be, what experience she or he may have, and at the same time, you're grading everybody through the lens of your perfect image in your head. And that's a dangerous way to hire, because all the very good hires that I've personally done in my career were always surprises. And by definition, the people who really blossom in a corporation are typically the ones going to bring something that you don't expect. They need to have the foundation, of course, but the high performers are always going to surprise you by going that extra mile that you could not predict.
I see. Well, I threatened to turn the tables a little bit and ask you some questions. So in that, what you just said, it struck me that you're balancing two things, sort of an intuitive, sort of artistic or more holistic side of your personality against a more hard-nosed business, metric-driven type of thing. Are you conscious of that? Do you agree with the fact that you yourself are sort of operating in a multidisciplinary way? And is that a struggle for you, or is that a natural thing for you?
How about both? I think that, I'm very much aware of that dichotomy. Arguably, it's because there is a dynamo by two polar opposites of that energy. One which is more soft, grounded listening, another one that's a little bit more fact-driven, yes, results-oriented. And maybe in the Silicon Valley, the system, broadly defined with quotes, is optimized for producing results, and therefore most of the conversation is always driven, and mostly driven, I should say, on the result-producing, performance-driven conversation. And maybe this podcast is one way for me to find another voice, to connect with other like-minded people, mm-hmm, to reach out to maybe like a bottle in the ocean, especially at a time when I think that the Silicon Valley is bringing new technologies, augmented reality, artificial intelligence, which are on the cusp of bringing a very, very new wave of technology innovation than what we have seen for the past 30 years. You started with CCDs, got perfected data analysis, but now we are making data analysis machines and data decisioning machines into connected cars, for example, that are going to drive themselves.
Yes. Yeah. So ironically, one of the student projects at San Jose State did with, I think it was Volvo, had to do with self-driving cars and develop machine learning techniques for identifying obstructions and so on. And so that's clearly one of the threads of the future is, let me just put it this way. Let me ask you the question, can machines learn? Can machines think? This gets asked a lot.
Machines learning, yes, to the sense of talking. You and I have talked about poetry and semantics. If we define learning for a machine as a way that the algorithms that have been coded into the machine are able to improve over time by refining the analysis through a feedback loop, yes, that is being proven. And of course, now in complex business conversations around autonomous driving, my day job, or others, you talk a lot about those training data sets and how there's a feedback loop of improvement.
Yes.
Can machines think? That's crossing a different line. And I think that what is thought, what is surprise?
Sure.
I really believe, and maybe that's an underlying theme of this podcast, which I'm curious about, is what separates us as humans from machines. And I think what is the question and the ability of humans to make decisions with imperfect information, love, feeling, risk-taking, making a decision with an incomplete set of information, while a machine, unless and one day it's coded to accept a certain degree of error, until it crosses that threshold, we are still in the machine functioning under its machine-based algorithms.
Yeah, yes, I see you. Let me tell you a little story that I think is relevant. Deep learning. The first time I heard the term deep learning, I thought myself, wow, what is this? It must be, with a name like that, it's got to be some profound advance. And then I got very skeptical of it with some help from my friends in the Stanford statistics department and so on. Deep learning is just many layers in neural networks, basically. And it makes the problem of interpreting what's going on inside a neural net even harder rather than easier. So I had a very skeptical view of how important deep learning would be. And it's a great way to solve specific problems like identifying zip codes on scrawled envelopes in the mail system. That's the archetypal example of that. But going beyond that, never. And then I heard a talk by a really bright group at Stanford that was using deep learning in a way I don't have time to go into, but it's a fascinating story of gravitational lensing, where strong gravitational fields actually bend light and distort the light, and undoing the distorted image to figure out what the original source looked like is a big problem. And to make a long story short, they did an experiment where after training this neural network on some data, they exposed the network to some data that had properties that were never represented in the training data, and it solved that extra problem just as easily as the original problem. So in other words, it went beyond the scope of the training data, and it's the simplest way of saying it. And right there in a 40-minute talk, I was convinced that there's more to deep learning than I gave credit for. So it's not the same as machines thinking, but it's learning beyond what you feed it in the way of training data, I think is kind of like learning. So
all right.
Anyway,
we have crossed a lot of thoughts from your beginnings as an astronomer to your work in the Silicon Valley and NASA AMES, to learning with new brains. So the next episode will focus on the beginnings of human psychology. Actually, I'll talk a little bit about the construction of the psychology of human beings. So the second season will focus on the key triggers and drives of the human psyche. And in the episode after, I'll interview someone who will talk to us about his personal experience from the beginnings, precisely, and what led him to be an entrepreneur. Jeff, thank you so much for your time today. It was a pleasure having you as our first guest in this conversation. around hit pause. Thank you again, and maybe we'll come back to you to explore this deep thinking and deep neural networks.
Sure. Thank you, Hervé. It was a pleasure and an honor to participate.
This podcast is a simple way of sharing my thoughts. It is a personal endeavor, nothing more. A way to connect. The views and opinions represented in this podcast are solely mine. They are in no way, nor should they be assumed to be shared, supported, endorsed by my employer, the sponsors of this show, Anchor.fm, where it is hosted, and all the distributors thereof. You may find more information, links, pictures, videos, documents, and more, which may have been referenced in this podcast on my website at www.utesa.com/podcast. There, it feels so much better after saying all of this. And so, it's time to part ways, at least for now. Until next time, time to say goodnight, time to hit pause.